class, today we're going to start section 3, which is the molecular interpretation of entropy. Now this lesson is going to be a little bit long, which is why this is the only thing that you guys are going to be doing today. So let's go ahead and get started. So let's kind of review what entropy is. Entropy, again, which is denoted by the letter S, is the degree of randomness in a system. When we covered what entropy was, we also said that it was related to the motion of molecules. In this section, this is where we're going to talk about those motion of molecules and how are they related to the randomness of a system. The key scientist in determining the entropy within the motion of molecules is Ludwig Boltzmann, and he gave that conceptual meaning at the molecular level. Now, just like we said in a previous slide, more random molecules or molecules that have more entropy are usually more spread out or they're traveling faster, such as the expansion of a gas. They spread out to fill a room, and gas particles have a lot of energy to move around pretty quickly. So let's start with an introduction for this section. The introduction is the scenario of the expansion of a gas into a vacuum, and we know this is a spontaneous reaction. We know this is a spontaneous process. We also now understand that since all spontaneous processes are irreversible, that this process is also irreversible. And based on the second law of thermodynamics, entropy of the universe increases during this expansion. Now, gas is a collection of particles that are constant random motion. So that's something that you should keep in mind as well. Gases have random motion. Here we have a scenario of expansion of a gas at the molecular level. We have two flasks, and they are joined to each other right here at something called a stopcock. Right now, the stopcock is closed, and then over here, they're going to be open. So before the stopcock is open, both molecules are confined to the left flask. We have a red and a blue molecule. When we open the stopcock, such as these four scenarios, the molecules travel randomly throughout the two flasks. So because they have their gases, they have random motion. All four of these arrangements are equally likely. For example, one in each flask, opposite one in each flask, both in the left, or they could both be in the right. All four arrangements are likely. For example, the probability of red on the left is 2 for 4 chances. For example, it's on the left here and it's on the left here. The probability of both on the left or the right is 2 out of 4 chances. And then we'll square it since there are two molecules, and that's about a 1/4 chance. If we had 3 gas molecules, we would find the probability that all 3 are on the left flask by cubing it, and that gives me about 1/8. And the more molecules you have, the more these different probabilities are going to get smaller, smaller, and smaller. You even have to consider a mole of a substance. Now, a mole of anything, remember, is 6.02 times 10 to the 23rd molecules. So the probability that all of them are going to stay on that left side is 1/2 to the nth. So the nth is going to be that 6.02 times 10 to the 23rd. And that's an extremely small number. And this tells us that molecules like to spread out, and that their most probable arrangement is they're usually spread out about equally in both flasks. Now, the stopcock opened, the arrangement of gas molecules is said to be more random because they can move all about it in a random order. They're disordered. And so, therefore, we can come to the conclusion that the more volume you have, the more randomness you have, as if we were just talking strictly volume. Okay. So this leads us into Boltzmann. He was that famous scientist, and he actually used statistics and came up with an area of science and chemistry known as statistical thermodynamics. This uses tools of statistics and probability to link our microscopic worlds of chemistry, in other words, to connect entropy to molecules. Now, this field of science is pretty complex, so I'll introduce you to the concepts, but we won't necessarily have to do the math. Now, a previous example showed the number of possible arrangements help explain why gas expands whenever we have a large volume. Now, at the microscopic level, the speed of each molecule tells us its kinetic energy as well. And then we came up with this term called microstates, which is denoted by the letter W. The definition is it's a single possible arrangement of the position and kinetic energies of a gas molecule when the gas is at a specific temperature and volume. So these different molecules can have different positions and different speeds because think about it, some are moving fast and some are moving slower. One thing I don't want you to get confused on is the difference between a state of a system and the microstate associated with the state. Remember, a state is the macroscopic view, macro meaning big, and this is characterized by pressure and temperature, whereas microstate has to do with things that are tiny, like the atoms or molecules that relate to a given state. The connection between the number of microstates that we just defined on the previous slide, denoted by the letter W, and entropy are expressed in what's called Boltzmann's equation. As we said previously, we won't be doing math. This is largely conceptual, but I'm just going to introduce you to it. Here, delta S, which is entropy, equals K, which is going to be Boltzmann's constant. You're going to have your microstates final minus Boltzmann constant times microstate initial. And then the Ln stands for natural log. This is located on your computer, your calculator. I'm not sure if you've gotten to natural logs in math class, but the one cool thing about natural logs is when you subtract them, it's the same thing as saying you're dividing them. So in other words, you could say is entropy is related to Boltzmann's constant times the natural log of your final microstates divided by your initial microstates. One thing that this equation tells us is that if your final microstates are bigger than your initial, we have a positive delta S. And this tells us that entropy increases with the number of microstates. So it relates microstates go up, entropy goes up. That allows us to take into other account or other variables and how they affect entropy as well. The number of microstates increase if you increase temperature because you're going to be moving faster and therefore entropy increases. If you increase the volume, entropy also increases as well because there is more randomness, more ways that molecules can move and more areas that they can move, so there are different microstates. And then if you decrease the pressure, one thing about pressure and volume is they go hand in hand with one another. They are inverse. So volume increases, pressure must decrease. Okay, and then the last one is the number of independently moving molecules. We saw a couple slides ago that molecules is 1/2 to the nth power. So the more molecules you have, the more random motion's going to be, the more spread out they're going to be as well. Sorry about that. So let's talk about molecular motions and energy. When a substance is heated, the motions of its molecules increase and therefore your kinetic energy increases. Remember, kinetic energy is proportional to temperature. I'm going to go ahead and star that. So the more temperature is, the faster these molecules move. Now, any real molecule can undergo 3 types of complex motion. And again, one thing I want to state here, and I have it bolded for a reason, molecules have greater number of microstates than atoms because molecules have more ways in which they can rotate around. So again, molecules have more microstates than atoms. So molecules exhibit several types of motions, and some of these that atoms cannot. One is translational. This is movement of the entire molecule from one place or another, and they move in one direction. Atoms can do that. You have vibrational, so atoms in a molecule move periodically toward and away from each other, and this has to do with electron repulsion. So what is pulling these together and what is pushing electrons apart? And then you have rotational, and then rotation is the rotation of a molecule around its axis, kind of like a planet rotates on its axis as well. Here, I'm going to go ahead and star this slide because most people are like, oh, it's just a picture. I don't need to write this down. But one thing you should write down is that solids have less entropy. And as you increase entropy all the way to a gas, gases have the highest entropy. Here, for example, we have a solid water, which is ice. This is a rigid crystalline structure. The only motion it can have is vibration, and so it has a very small number of microstates, so it's small entropy. Over here we have liquid water, so these water molecules are freed up a little bit. There's increased freedom, so we can do a little bit of translation, and we can vibrate a little and rotate. So we have a larger number of microstates. And then when you keep heating it up, increasing that temperature, we become water vapor in the gas phase. These molecules are a lot more spread out. They're independent of each other. They're free to have all these three different types of motions of translation, vibration, and rotation. So we have the largest number of microstates here. One thing people do have a question about is, yes, we have solid, liquid, and gases, but what do we do when it's a solution or when we dissolve something in water? Well, generally, when a solid is dissolved in a solvent, entropy is actually going to increase. Now, this is increase for the ions that we're dissolving. So I'm going to go ahead and star that. Water actually loses entropy because water is not as free to move around anymore. Instead, water is going to actually move around the ions of that compound and solvate it. But those ions are no longer in a solid compound. They are split apart, so they have a little bit more freedom. So ions actually have more entropy. One thing I want to add to this slide, and please add it to your notes, is generally if you're going from a gas to an aqueous solution, though, you are going to lose entropy. Before we get to the practice problems, the other thing I want you to consider is entropy in the number of moles. Here we have the following reaction. We have nitrogen monoxide plus oxygen gas yields nitrogen dioxide. And here we have 2 moles and 1 mole, so it gives me 3 moles for reactants. In my product side, I only have 2 molecules or 2 moles. So whenever we have a decrease in the number of moles or molecules, there's usually a decrease in motion. There's not as many microstates, and therefore we decrease entropy. So decrease in number of molecules decreases entropy, and vice versa. So this slide, I have it bolded. It summarizes a lot of stuff that we just talked about in very nice, clear detail. In general, entropy increases when gases are formed from liquids and solids because gases are more spread out. Liquids or solutions are formed from solids. If the number of molecules increase or the number of moles increase. So here we're going to go predict the signs of our entropy value, whether they're going to be positive or negative based on what we're given. So now we need to look at this from reactants to products. What happens when it goes from a reactant to a product? Does it gain or lose randomness? So in letter A, if you look at these two things, the only thing different about them is the state of matter. One is a liquid and one is a gas. So remember, if you go from a liquid to a gas, gases move around a lot more. They have more different microstates. So this is going to be a positive value. If you look at letter B, there are 2 things that can help give you away. One is here you have 1 mole, Here you have 1 mole. So that's 2 moles. And then over here you just have 1 mole. So you go from 2 moles to 1 mole. You're decreasing, which would make you have a negative entropy value. Oops, negative. The other thing you can look at is your states of matter. You're going from an aqueous solution where these ions are spread farther apart to solid where they're closely packed together. They can't move very well. So whenever you go to aqueous to solid, it's also going to be negative as well. Looking at letter C, there are a couple things you can look at. The first thing you can look at is the number of moles. Here you have 4 moles and 3 moles, that's 7. And your product side only has 2, so that's a negative because my moles went down. The other thing that you can look at is your states of matter. So here I have a solid turning into a solid. Not that big of a deal, but here we have a gas going to a solid. So it has to lose randomness and become more orderly to form that solid. So that is another way we can get that negative. And the last one, there are a couple things you can look at. Here we have 1 mole plus 1 mole gives me 2 moles for reactants, 2 moles for products. Well, that doesn't tell me anything about it being positive and negative. If I look at my state of matter, they're all gases, so that doesn't tell me anything. In fact, based on the information we have been given, we cannot determine. And if you look at the examples in your book, which is the book I teach out of, they actually put that as the answer. We cannot determine based on the information we've been given. So here are a couple other ones that I want you to try. So why don't you kind of pause this video and see whether you can determine whether they're positive or negative based on what is happening in the following equations. Okay, so let's kind of go over the answers. On the first one, notice that the moles are the same, the compound is the same, so the one thing you have to focus on are the states of matter. And it's going to a gas, so this is going to be positive, hopefully is what you put. On the second one, there are 2 things you could look at. You could look at, we have 2 reactants and 1 product, so we know that it's decreasing. The other thing that you could have looked at is here we have a gas going to a solid, also making it negative as well. For letter C, again, there are 2 things you can look at. You can see that I have 2 reactants to 1 product. So again, that is negative. It's decreasing. The other thing you could have looked at is you have 2 gases losing energy to form a solid. And the very last one, letter D, here we have 2 and 1, so that's 3 for my reactants, and then 2 for my products. So if we look at just that, we went from 3 to 2. I am decreasing. That is negative as well. We can't really look at the states of matter because they're all the same. The other thing that this book allows you to do in other examples or other ways you may see questions being asked is if I was given a pair of things, how would you be able to tell me which one has greater entropy? Here, this is one where you're going to have to focus on the moles, the temperature, even the pressure. Before we get started, one thing I do want to tell you is some questions are going to ask you about STP. That stands for standard, temperature, and pressure. Temperature is about 0 degrees Celsius. Pressure is 1 atm. So let's get started and let's kind of explain these. Here for letter A, we have 1 mole of salt in a solid form, or 1 mole of hydrochloric acid in gaseous form, and both of them are at 25 degrees Celsius. Well, here we need to look for the difference. The temperature is the same. The number of moles are the same. So here we can look at our state of matter. One is a solid and one is a gas. Well, based on the state of matter, HCl is actually going to have more entropy because of the state of matter that it's in. Okay. Letter B. we have 2 moles of HCl in gas form or 1 mole of HCl in gas form, and both of them are at 25 degrees Celsius. So both of them are at 25. Both of them are gases. So here the only difference here we have 2 moles versus 1 moles. Remember, the more moles we have, the higher the entropy value. And letter C, we have 1 mole of NaCl in aqueous form and 1 mole of NaCl in solid form, and both of them are at 298 Kelvin. We'll notice that the moles are the same, the temperature is the same, the only difference is aqueous and solid. Remember, aqueous solutions are always going to have greater entropy, generally speaking. Here, I want you to try for each pair of these, choose which one has greater entropy, and kind of try to explain why to the best of your ability. So for letter A, B, and C, go ahead and solve these. Pause the video and see what you come up with. Okay, going over for the answers for letter A, we have 1 mole of hydrogen gas at STP, or 1 mole of hydrogen gas at 100 degrees Celsius at 5 atm. So here, let's look at the difference. They're both in gaseous form, so I can't take that into account. They're both 1 mole. So here we have to look at STP. Remember, that's standard temp and pressure. That's 0 degrees Celsius. 0 degrees Celsius or 1 atm. Here we can look at our pressure or our temperature increasing and our pressure decreases. So if you actually flip back very long ago where I told you write down this one, here we have an increase in temperature, decrease in pressure. Remember, that is entropy increasing. So remember, don't forget to write down that slide. So if our temperature increased, our pressure decreased, the one that is going to be correct is the 1 mole of H2 gas at 100 degrees Celsius. Part B, we have 1 mole of solid water at 0 degrees Celsius and 1 mole of liquid water at 25 degrees Celsius. There are 2 things different here. One is the state of matter and one is the temperature. Here my temperature is increasing. My state of matter is also becoming a liquid, so they're able to move around more. That's going to have more entropy. And the last one, we have 1 mole of dinitrogen tetraoxide in gaseous form at STP, or 2 moles of nitrogen dioxide in gaseous form at STP. So temperature and pressure we don't care about. They're both gases. So if we look at the moles, NO2 has more moles, so therefore it would have greater entropy as well. This brings us into our third law of thermodynamics. There are 3. We've learned about the first, second, now the third. If we decrease the thermal energy of a system by lowering the temperature, what happens is we lose kinetic energy and it becomes stored. It decreases. There's no more translational, vibrational, or rotational energy. It's slower and slower. So as less energy is stored, the entropy of the system decreases. So the third law states the entropy of a pure crystalline substance, which is a solid, at absolute 0 is 0. So in other words, if you have 0 entropy, your temperature is 0 Kelvin. No molecules have thermal energy, and there's only one possible microstate. And if you really wanted to check it, you could throw it into that Boltzmann equation and find out that it has no entropy. I like this little picture because it shows how if you increase the temperature, entropy also increases. Notice 0 entropy, 0 Kelvin. And that brings us into the last topic of this section, entropy in the human society. Now, the third law, the laws of thermodynamics have profound implications on our existence. They dictate a lot of things we do. But living organisms like ourselves are pretty highly ordered. This seems to violate that second law about things being random. Well, even though we try to create order in this world, there are thousands of chemical reactions that we have within our body in order to maintain life, such as cellular respiration, making proteins, breaking down proteins, and these reactions increase the entropy of the universe. So overall, even though we try to spend a great deal of energy trying to fight the second law of thermodynamics and making things more orderly, for every piece of order that we create, we've also created more randomness and disorder based on chemical reactions. Even everyday things like going around in a car, we do combustions of fuels, releasing CO2 and water and heat into the air. So while we do seem like very ordered human beings and we try to keep things orderly, if you think about it, even if we try to keep our bedroom orderly, over time it's going to become messy if we don't expend that energy in order to keep it that way, keep it clean. So we do not violate the second law. And that's the end of today's lesson. Let me know if you have any questions, and I'll be more than happy to help. And I hope you guys have a good day.